Okay, so picture this, right? You're trying to climb a mountain.
Right.
Sometimes good old hiking boots, solid, dependable.
Yeah.
You need to reach the top.
Sure.
But what if this mountain is like all shifting sand and every path you take just disappears? Suddenly those boots don't seem so helpful, huh?
Not really, no.
Well, in the world of computing, we've got a kind of similar challenge, you see.
Oh, okay.
When do you stick with the tried and true, those reliable hiking boots of classical computers?
Right.
And when do you need something a bit more experimental? Maybe even, dare I say, teleporting, like quantum computing. That's what we're diving into today.
Welcome back, everyone, to another deep dive into this incredible world where information meets, well, the very fabric of reality.
It's pretty mind-blowing when you think about it.
It is. It is.
We've been digging deep into some really fascinating research papers.
Oh, absolutely.
And articles, really trying to get to the bottom of this.
Yeah.
This whole classical versus quantum question. And our mission today is to give you a clear understanding of when to use which.
When each one really shines.
Exactly. Cut through the hype and all that.
Absolutely.
So before we get into the nitty-gritty, let's just lay down a basic mental picture.
Okay.
Right? Think of classical computers like they're working with bits.
Okay.
These are tiny little switches, on or off, a 0 or a 1, very clear cut. They process everything step by step, very predictable.
Makes sense.
Quantum computers, on the other hand, they're different. They're using these things called qubits.
Right.
And these qubits, well, they could be a 0, a 1, or both at the same time.
Now that's where it gets interesting.
It does. It does.
It's superposition.
Exactly. A key concept in quantum computing.
One of them.
And then you've got entanglement.
Oh, yes.
Where these qubits are linked, but in a really weird way.
Yeah.
Like, you know the state of one, you instantly know the state of the other.
Spooky action at a distance.
It's mind-boggling.
It is. It is.
No matter how far apart they are.
Absolutely.
So, with that in mind, let's dive deeper.
Oh, let's do it.
Let's figure out when to use which tool.
All right.
Okay, let's start with the foundation.
The basic.
Classical computing, the workhorse.
Yeah.
As we said, built on bits at 0 or 1, and they're manipulated by logic gates.
It's like a huge network of switches.
It is. Making decisions, yep.
Yeah.
And, like those hiking boots, it's dependable.
Yeah.
Give it the same input, same output.
Every turn.
Every single time.
Reliable.
Like a well-marked path. You know where you're going.
Yeah.
Now, quantum computing.
Yeah.
The new kid on the block.
The explorer.
Yeah.
The one forging new paths.
Yeah. Instead of bits, we have those qubits.
Right.
Which can be both 0 and 1 at the same time.
Superposition.
Superposition. Yeah, it's like
a spinning coin.
Yeah, like a spinning coin. You don't know if it's heads or tails
until it lands.
Until it lands, exactly.
And then you got entanglement.
Entanglement, oh boy.
Where you've got two of these spinning coins.
Right.
And as soon as one lands heads, the other one lands tails.
Even if they're miles apart?
Yeah, or even light years apart.
It's crazy.
It is, it is.
It's like they're connected by some invisible force.
Absolutely.
And unlike classical, which is very deterministic, quantum, it's probabilistic.
Yeah.
You don't get one answer, you get a whole range of possibilities.
Like a landscape of potential outcomes.
Yeah, and each one has a certain probability.
It's more like, a high-performance race car.
It is.
Powerful, but you need a skilled driver.
And the right track.
Absolutely.
You wouldn't take a Formula One car through a city center, would you?
Not unless you were making a film, maybe.
Uh-huh. Yeah, good point.
But you see, it's all about picking the right tool for the job.
It is.
And that probabilistic nature of quantum computing, that's really important to remember. Because you might have to run a quantum algorithm multiple times to get, a statistically significant result.
Right, to build up a good picture.
Exactly.
Okay, so let's get down to it.
Let's break it down.
Strengths and weaknesses.
Head to head.
What can classical computers do really well? Where do they struggle?
Yeah.
And where does quantum start to look like the better option?
Right.
Let's start with classical.
Okay.
One of its biggest strengths is its versatility.
Like a Swiss Army knife.
It is. It really is.
It can handle anything.
From writing an email.
To simulating the climate.
Exactly. It's incredible.
And it's incredibly reliable.
Yeah, that deterministic nature.
Yeah.
You can trust the results.
Absolutely.
Whether you're balancing your checkbook or
relying on the braking system in your car.
Exactly. It's just there.
And the technology is so mature.
It is. Decades of development.
Yeah.
Refining the hardware, the software.
It's robust, accessible, affordable.
And the scalability. billions of transistors on a single chip.
It's mind-boggling.
It is. It is.
But even the best Swiss Army knife has its limitations.
It does. Where does it struggle?
Well, when you're faced with problems with a huge number of potential solutions.
Like trying to crack a really complex code.
Yeah, or simulating the interaction of atoms in a large molecule.
Right. So many possibilities.
Yeah, it could take longer than the universe exists to find the answer.
That's the problem with exponential complexity.
Yeah, the time and resources just explode as the problem gets bigger.
And then there's the energy consumption.
Oh, yeah, those huge AI models.
They need so much power.
Pushing classical systems to their limits.
It's a real concern.
It is.
Okay, let's look at quantum.
Right.
One of its strengths is that parallelism.
It can explore many possibilities at once.
Yeah, like trying multiple keys on a giant keyring at the same time.
Instead of one by one.
Exactly. That makes it super powerful for things like optimization problems.
Finding the best route for deliveries, that sort of thing.
Right. Or searching through massive data sets.
Much faster than classical methods.
It's really good at simulating quantum systems, too.
Yeah, things like molecules and chemical reactions.
Stuff that's really difficult for classical computers.
They're trying to use classical rules to mimic a quantum world.
Right. It's like trying to describe colors to someone who's never seen them.
Yeah, good analogy.
Quantum computers, they speak the same language.
Absolutely.
And we can't forget about cryptography.
Oh, yeah. Shor's algorithm.
That could potentially break a lot of our current encryption.
Yeah, big implications for security.
It's a bit of a double-edged sword, though, isn't it?
It is.
Because quantum computers are also driving research into new types of encryption.
Quantum-safe cryptography, protecting us from both classical and quantum attacks.
It's a whole new world.
It is, it is.
But quantum computing does have its challenges.
Oh, yeah, for sure.
Those qubits, they're delicate.
Very sensitive to their environment.
Susceptible to decoherence.
Losing their quantum properties.
Leading to errors.
It's a big engineering challenge to keep them stable.
It is, and unlike classical computers, which can handle all sorts of tasks.
General purpose machines.
Quantum computers, they're more specialized.
They're only good for certain types of problems.
They're not going to be replacing our smartphones anytime soon.
No, not yet anyway.
And scalability is an issue.
Building quantum computers with lots of qubits.
That are stable and well-connected.
It's a massive undertaking.
And developing quantum algorithms.
You need a deep understanding of both quantum mechanics and computer science.
It's not easy.
It's not for the faint of heart.
So when does classical computing still rule?
Okay, well, for most of what you do every day, classical computing is more than enough.
Like browsing the web, streaming videos,
sending emails, social media.
It's all handled efficiently by classical systems.
Using a quantum computer for those things would be like using a rocket to go to the grocery store.
It's overkill.
Completely.
And all the usual office stuff.
Word processing, spreadsheets.
Presentations.
All classical.
Even gaming.
Even with all those fancy graphics.
It's still all classical.
Quantum computing just isn't there yet for those kinds of applications.
I can't imagine playing a video game on a quantum computer.
It would be interesting, though.
It would, wouldn't it?
But not very practical.
And data processing and analysis?
Databases, statistics, machine learning.
All classical.
Our classical algorithms and hardware are very good at those tasks.
What about AI?
Well, the AI we have now, things like image recognition and chatbots, they mainly run on classical hardware.
Especially with those powerful GPUs?
Graphics processing units?
Right. They're really good at parallel processing.
They are.
Quantum machine learning is still mostly theoretical.
Yeah, it's an area of active research, but it's not mainstream yet.
Okay, so when does quantum computing really shine?
All right, one area is cryptography and security.
As we said, it could break a lot of our current encryption.
Yeah, which is a big concern.
But it also drives research into new quantum-safe encryption.
That's the other side of the coin.
Exactly. So it's a bit of a race.
It is a race to stay ahead of the curve.
Another area is drug discovery and materials science.
Simulating molecules and chemical reactions.
That's really hard for classical computers.
But quantum computers are naturally suited for it.
They can speed up the discovery of new drugs and materials.
Imagine new treatments for diseases.
Or new materials that could revolutionize industries.
The possibilities are vast.
It's pretty exciting.
It is, it is.
What about optimization problems?
Things like logistics, finance, airline scheduling.
Quantum computers could find better solutions.
Leading to cost savings and greater efficiency.
And that could benefit everyone.
Absolutely.
And we can't forget the potential for quantum machine learning.
Yeah, it could revolutionize AI.
Speed up training, find hidden patterns.
Things that classical computers might miss.
It's a lot to look forward to.
It is. It is.
But there are some gray areas, right?
Yes, where it's not always clear which approach is best.
Tell me more.
Well, take search algorithms.
Okay.
For small data sets, classical algorithms are fine.
They work well.
But for massive, unsorted data sets,
Like the entire internet.
Grover's algorithm, a quantum algorithm, it offers a quadratic speedup.
So it's faster, but not exponentially faster.
Right, but it can still save a lot of time.
Especially when you're dealing with huge amounts of data.
Absolutely.
What about optimization tasks?
Classical computers have good approximation algorithms.
So they can find decent solutions.
Yeah, good enough for many practical purposes.
But for really complex problems,
With lots of variables.
quantum techniques like quantum annealing,
Or QAOA.
QAOA, right?
They might find even better solutions.
Leading to greater efficiency
Makes sense.
and simulations.
For classical systems, like weather forecasting,
Yeah.
classical computers are usually good.
But for quantum systems,
Things like electron behavior or molecular dynamics.
quantum computers have the edge.
They're simulating,
It makes sense.
It does.
So looking ahead, what's important to understand about quantum computing?
Well, one concept is quantum supremacy.
We hear that a lot.
It's when a quantum computer can do something that no classical computer can.
In any reasonable time frame.
Right, like Google's Sycamore processor.
That random sampling problem
Much faster than any classical computer could.
is a big milestone.
It showed the potential of quantum computing.
But the real goal is quantum advantage.
When a quantum computer outperforms classical on a practical problem.
That has real-world benefits.
Exactly.
We're not quite there yet, but it's what everyone's working towards.
It's the ultimate goal.
And current quantum computers are still noisy.
Prone to errors.
How do we overcome that?
Error correction is key.
Right, because qubits are so sensitive.
We need ways to detect and correct errors.
To build more reliable quantum computers.
That can tackle complex problems.
It's a tough challenge.
It is, but scientists are making progress.
And we also need to build larger quantum systems.
With more qubits.
That are stable and well-connected.
It's a huge engineering feat.
But one promising strategy is hybrid quantum classical computing.
Combining the best of both worlds.
How would that work?
You'd have a classical computer managing the overall workflow.
Okay.
And then offload certain tasks to a quantum processor.
Like the really computationally intensive stuff.
Exactly. It's a collaborative approach.
Using each type of computer for what it's good at.
That's the idea.
It sounds like a smart way to move forward.
It does. It does.
So if you're facing a complex problem,
And you're wondering whether to go classical or quantum.
what questions should you ask?
Okay, first, is the problem well-structured and deterministic?
If so, classical is probably the way to go.
Yeah, it's simpler and usually cheaper.
Second, does it involve searching a huge data set or finding an optimal solution?
Quantum might have an advantage there.
Especially as the technology matures.
Right.
Third, are you simulating a quantum system?
If so, quantum computers are the natural choice.
Fourth, is the problem small enough for classical to handle efficiently?
If so, stick with classical.
It's the easier option.
Absolutely.
And finally, do you need a definite answer, or is a probabilistic one okay?
Classical for certainty, quantum for possibilities.
That's a great checklist.
It is. It should help you decide.
So, to wrap up,
Yeah.
classical and quantum computing, they're not competing.
They're complementary.
Each has its strengths.
And they work well together.
Classical will continue to be essential.
For our everyday lives and many scientific tasks.
But quantum offers the potential to solve problems that are impossible for classical.
And hybrid systems are a promising way to start using quantum now.
It's an exciting time to be following this field.
It is. It is.
It makes you wonder how quantum computing will change the world.
In ways we can't even imagine yet.
What challenges will we overcome?
What new possibilities will emerge?
It's a lot to think about.
It is. It is.
Thank you for joining us on this deep dive into classical and quantum computing.
We hope you found it insightful.
Keep exploring the world of technology. It's always changing.
Until next time.
Goodbye.
Goodbye.